If you remember, we were talking a little bit about the presence of prepeaks. That was, I think, the last transparency. We're talking about the missing features and the importance of taking care and using additional techniques when you only rely on pair information, even if it's extracted from very good experiments, diffraction experiments, right? To see an experimental example, I chose here this problem that is actually C12 tab. This is a typical surfactant. This is a molecule that has a polar tail or an apolar tail and a head that is hydrophilic, right, or is charged. And so in this solvent that is called ethylene, right? And typically when you increase the concentration of the surfactant, what you see, this is a small angle X-ray experiment. Small angle because you see wave numbers are very, very small. They are below 10 to minus 1 angstrom, inverse angstroms, and this is typically what is called small angle, right? You see that as you add more and more surfactant, you have the presence of this prepeak. Well, this state corresponds to this picture that you see here using optical microscopy. That's the formation of micelles. Ethylene stays outside, and then the micelles have the polar part pointing towards ethylene, and the apolar part, they want to just be together, right? So the only thing I'm trying to indicate here, this is plenty of examples, and using the small angle X-ray scattering particularly, you can do it with neutrons, but it's a sophisticated technique and expensive that you can solve with using small angle. You have lab equipment to perform small angle X-ray scattering if you have sufficient sample. Otherwise, you go to a synchrotron. And there are plenty of examples where you will see this process of self-aggregation, of the buildup of supramolecular structures from more or less complex molecules. In this case, a surfactant. If you look at the molecule, this is a rather complicated molecule, but it's still a molecule. And there you have supramolecular structures, right?
The fact that usually when you have surfactant, they polydisperse. So the
yeah.
polydisperse is the reason for it being the peak
yeah.
more wide.
That's the reason, because, I mean, the peak doesn't look that wide here,
yeah.
but it is, because this is log scale.
Yeah.
So the peak actually goes over not an order of magnitude, but almost. And you see here that this is very, very, very polydispersed. That's the case of surfactants. Notice that in the case that we studied before, here, the clusters are not that much polydispersed. Actually, if you look at the distribution of clusters here, you see that this is a beta-shaped distribution that is relatively narrow. And that's because of the particular type of interaction that has this feature that I drove you yesterday. That has this maximum when you have the equilibrium between repulsive and attractive forces, right? So it's much more controlled in this respect. Some systems actually form micelles of definite shape, and in nature you can find them. It's, for instance, proteins, they actually aggregate with less polydispersity than the one you see here, because here you see droplets. This looks like a condensation process, only that they remain stable. For whatever time you keep the sample, this will not phase separate. If you have a condensation process, this will be a transient state. The small bubbles will be attracted by the large bubbles, and they will merge. Why this doesn't happen? Because there's repulsion between them. You know, if you have, for instance, the charged part in the outside, well, here you have two charged parts. So they do not have tendency to merge. Okay, now let's go to explicitly take a look at how do the structure factor looks for mixtures. The simplest case, binary mixture, two-component system. Well, here you can do the splitting. I mean, this is the formula we saw yesterday, right? Or when we already have gotten rid of the module here. We have expanded this term into this. Recall, never do that on the computer, because this is a waste of time. This is order squared, n squared operation. And if you have two components, you can separate this in one term that depends on the alpha particles, one term that depends on the beta particles, and a cross term, right? So this is just simple algebra. Actually, these terms can be named in this way, and you call this the alpha-alpha structure particle. That is the partial structure factor for the alpha component, the partial for the beta, and the cross term. They are built in such a way, so they are connected with the pair distribution functions like these, and they are built in such a way that these quantities that are not cross terms go to, in the limit, towards the mole fraction, just by definition. You do it like that by definition. It goes to the mole fraction. Whereas the cross term goes to 0. That's the reason for this delta. The reason to do this is that once you add all the terms, you end up with a total. So that's the tricky thing, the way you build this, because when you perform the addition, the sum of the partials gets the total. In some cases, they use other definitions that do not fit this. But I prefer to use this definition, and it's the sort of the standard. If you do the Fourier inversion of this, you end up with what is called the average pair distribution function, the weighted average. And why is weighted? Because you have the partial pair distribution functions, that is species pair distribution function, the cross terms, but they are weighted by their concentrations and by their scattering lengths. So this is what you get from a diffraction experiment. You don't get the components. You get this sort of mix-up. So we will learn later on how to separate if it is possible. Not always possible. And you can do it in neutron scattering. In X-ray scattering using synchrotron, there is a technique which is called near-edge X-ray scattering that allows to perform certain separation, but it's not very precise. I think it became fashionable 20 years ago, but it died out because it doesn't provide sufficient precision. So people, well, is satisfied with whatever they have. This is an example that we did 15 years ago, where we actually did the neutron, the X-ray scattering in molten mixtures of selenium and tellurium, right? And we extracted these average functions here, and then you can see how they change depending on the temperature, right? These are molecular dynamics results, because here it is impossible to separate. That's in order to separate, we tried, and we checked for the prices of different isotopes, and we were horrified. So that was out of the question, because the key problem is, can you have access to different isotopes for each component and separate? We will see later on how to do it. And the main problem is sometimes you do not have isotopes available, or the price is prohibitive. So in the case, for instance, selenium was more or less okay, but tellurium was something like...
and if you change concentration, cannot get a grasp?
You might get a grasp, but the problem is that everything is correlated, so the function itself depends on concentration. So what you get is something different. The pair distribution function for the pure component is not the same as the pair distribution function for the component which is 50% in concentration of the other one. So that's the main problem, right? Okay, this is a special kind of mixture, so to speak, molecular fluids. In the sense that, well, you have two atoms, and these two atoms also might be different. But the first thing we are going to consider is just, well, this is a homonuclear case. What's the effect of performing a scattering experiment, for instance, on chlorine, nitrogen, and you just consider the bonds rigid. Forget about vibrations, right? That's a simple case. Well, if you consider that, you actually have this bond separation, this dy, right? Well, you actually can split the scattering factor, the structure factor, into terms. One term that depends on the atom-atom distance. This would be sort of the contribution from the intermolecular correlations, atom-atom intermolecular correlations, plus another term that comes from correlations within the same molecule. Is this one. So we separate this into intermolecular and intramolecular correlation. If we assume that this is a rigid bond, that's kind of simple because the G of R, the pair distribution function of a rigid bond, is obviously a delta function because that you only have one distance, d, that's it. What's the Fourier transform of a delta function? This one, right? So what you have, the result of this is that you will have a long wavelength oscillation that is decaying, right? Let's take a look. This is simulation. I think it was for nitrogen, right? Here you see it. And if you look at the pair distribution function, ignoring the molecules, this is just atoms, nitrogens, what you get is a huge peak here. It's not really a delta function because you have certain splitting due to the positions, but it's a huge peak, and then you have the rest, that is the intermolecular contribution. When you transform, okay, you have that term over there. If you want to consider vibrations, it is possible. You end up with a factor like that. That's the famous Debye-Waller, again, that reflects thermal vibrations of the bond. And this is what you see in a real experiment. This term, the sine Q with a Debye-Waller, is this oscillation. And these dots are the neutron scattering experiment. The short wavelength, obviously, you get it completely wrong. But look at here. These long wavelength oscillations come precisely from the bond. And again, see the correspondence between Fourier space and real space. The long wavelength oscillations occur at large Q values. That means they are detecting a feature that happens at small r bond distance, right? So it's always the same thing. That's the reason why it is the reciprocal space, right? Okay, in the case, and you have large entities like polymers or colloids, you don't do that. You just simply do the same thing as you do when you do X-rays. When you do X-rays, you do not consider electrons separately. You know that electrons are the scatterers. It's not the nucleus. But all the scattering of all the electrons of a single atom gets embedded into a single function that is the form factor. When you have a polymer that has hundreds or even thousands of atoms, in the case of a protein, for instance, you do not consider separate things, separate contributions, but you put them all together into a form factor that you will call the F intramolecular contribution, F of Q, that you have to calculate in advance, right? That's the way to handle it, right? I mean, from the experimental point of view, having a molecular fluid is the same as having a mixture, because in the case, for instance, of neutrons or X-rays, they do not distinguish. They simply see atoms here, whether they are vibrating or not. So we still are left with the question, how do you separate the contributions? Imagine that you are performing an experiment. Well, chlorine, you don't have the problem because you have the two atoms are identical. But if you have, for instance, hydrogen chloride, well, put deuterium because otherwise if you have hydrogen, you're screwed up. But put deuterium. How you separate the deuterium and the chlorine contributions? Well, this is a classical example. We have a salt in a deuterated water, heavy water solution, right? and that's from the Enderby, who is one of the fathers of neutron scattering science, right? His book is one of the most cited references. Well, typically, here you have the possibility. Isotopes are not that expensive. So you have 2 isotopes for chlorine and 2 isotopes for lithium. Here you have the abundance, and you have the scattering lengths that are, well, relatively different, significantly different. Okay, what can we do? You apply this difference method for isotopic substitution, which is basically you build these differences, right, where all these constants are here. One is these are all molar fractions from the M component, the X component, the D component, or the O component, right? You have all these combinations there. So you do this in theory. These are the quantities that you are actually combining. The factors A and B are proportional to the mole fraction of M. Recall that M is the cation in the salt, right? And C and D are proportional to M squared. Well, this is telling you something. If you have high dilution, you can get rid of C and D, which simplifies the problem. You always should try to simplify the problem in this case, right? High dilution, you only have A's and B's. With these combinations, you can construct these 2 functions, gm and gx, from the experimental data. These weighted functions, the gr are the ones you are getting. And these 2 functions are just, actually, this one, they have a common term. And here, these are terms that are salt-solvent correlations. So the G represents correlations between the oxygen and the deuterium, that means the solvent, the water, and the M and the GX, the correlations with the anion, right? If you have more components, you have to use a second-order difference method that requires 3 or 6 types of isotopic states. So things get much more component. You have to perform these differences, delta M1, delta M2, right? And the same for the other quantities. And in this way, you end up with the possibility to separate actually the contribution between the MM, for instance, that will be the cation-cation, or the anion-anion scattering factor. But you have to have money enough to buy 6 different isotopes, which is not always possible. 4 to get the cross term, and so the method is really efficient, but it's only used in very, very, very special cases. But that's the way you have to handle things. Sometimes you might be lucky. In the hands-on, we will see a case when there is a large difference between one isotope and the other. And in this way, you just can see immediately the contribution to the scattering factor because it dominates everything, right? This is an interesting example that we also did many years ago working with experimentals. Well, this is in Portuguese because we were collaborating with people in Lisbon. So I simply stole a part of the transparencies from the slide from them. This pillared clays is a particular case of, clays are layered materials. The problem they have is that they are not stable. So if you want to use them for adsorption, for instance, to make filters or to absorb hydrogen or gases for industrial purposes, they are not really stable because you don't have, when they absorb the material, they swallow. They just simply swell, they swell, they become bigger. And you don't want that. They become unstable and so on. The way to solve that is to put pillars in the middle. And pillars are, well, these are structures made of aluminum, and you put some chemical in here, you calcinate the whole thing, and the pillars get glued to the layers. And in this way, they just fix the layering distance. To obtain this distance between the two layers, that's kind of easy because that's regular. So you will have a perfect diffraction peak precisely at 2 pi divided by that distance. But what about if you want to see what's the distance between the pillars? Then you are in trouble, because that's a complicated problem. How can you do it? Because normally the pillars are not uniformly distributed. Well, to that we have this technique that is used for many things, mainly connected with absorption, that is called contrast matching, right? Okay, contrast matching, the interlayer spacing, for instance, this is what you see. These peaks for the different samples. The peak comes from the interlaying spacing. That one does not create any problem. But if you want the pillar distribution, well, you do this trick. You can calculate what's the scattering length, or the scattering factor, of the pillar, because you know the composition of the pillar, right? And taking into account that you can mix deuterated water with water, and the coherent length of the deuterated water is this one, and that of hydrogen is negative, you can play with the combination of water and deuterated water so that the coherent length of the material that is inside this mixture matches that of the pillars. If you do that, what happens is that for neutrons, or for X-rays, or in this case it will be neutrons, they would see a continuum, because the mixture of the deuterated water and water has exactly the same average scattering length that the pillar. So if there is a peak in the empty material due to the distribution of pillars, this peak should disappear when you put when this mixture of water and heavy water. Okay, so here you have it. This is the peak, and you start to add water with different compositions until finally you kill it. So this is the contrast matched layers. For neutrons now, all that is inside between the layers is a continuum. And because this water plus heavy water plays the same role as the pillars.
With the same concentration, is there anything to do with the concentration of the solution of water and heavy water?
Yeah. Because you mix, you mix until you fit it. Okay. You know, you have this term, and you have this term. And then you have all contribution from layers and whatever. So what you want is actually that these two terms, match completely that of the layers and the pillar. Oh. It's like you fill it with the same material, but disordered. But it's, for neutrons, it's the same material. Because on the average, what this is, something that is scattering neutrons in the same way.
Almost as the pillars were...
a continuum solid.
What you actually have there is water.
Is water and heavy water. So this is a rather sophisticated and interesting technique that is used for special cases when you have features to which you do not have access, and you can play around with something. As I mentioned, sometimes things are a damnation, sometimes are a blessing. This negative scattering length of hydrogen is bad, but thanks to that, you combine heavy water, and you end up having a material which can match almost anything, as long as you can use water. For some systems, you cannot, right? But you can play around with isotopes, obviously. Okay, let's go to a bit of the basics and try to sort of relate what we have seen with basic statistical mechanics, right? Well, these are terms that you probably know. This is a partition function. That's the definition of the n-body density, right? Of which we are interested in the one particle density and the two particle density, right? So here you restrict the summation to 1, this n to 1 or to 2, and you have this one, right? The two particle density distribution, if you divide that by the that of an uncorrelated system where density distributions are independent, so that's the product, you have the corresponding per distribution function, right? These are densities, this is distribution function. And this obviously goes to 1 because for infinite separation, probabilities become independent and you can use a product here and a product down here, right? Okay. If you look at the fluctuation here, you integrate over this term, that's a fluctuation in density. Yeah? You integrate, you end up with this average of n squared minus n squared, right? And this means that if you translate this into g of r, divided by n squared, you have the fluctuation of n, this is the fluctuation in the number of particles, divided by the average number of particles. Well, actually, this means that this integral, that's the limit of q going to 0, and this is telling you that the limit of q going to 0, small wave numbers, it represents the fluctuations in density. So what are the fluctuations in density? Well, if you do a little bit of basic calculus here, you can calculate the average number of particles using the partition function. You take this derivative, you end up with this fluctuation, and lo and behold, that's the compressibility. So that means that this limit is the fluctuation of densities, density fluctuation, sorry, which is actually the isothermal compressibility. That is telling you something that already was mentioned before. And this is called a sum rule. This is the sum rule because it has an integral of a correlation function leading to a quantity that actually is a macroscopic property. And this is the sum rule that connects structure and thermodynamics, right? If we now go to thermodynamics, there is a point where this derivative goes to 0 and the compressibility goes to infinity. Now we look at the question of the state, P versus volume, right? That's the standard for a gas. It goes this way, and here you reach a point where this becomes flat. That's the critical point, where the derivative of P with respect to V is 0. That means the derivative of P respect to V going to 0, infinite compressibility, and that is the critical point. That means divergence in the density fluctuations, that the fluctuations become, in density become macroscopic, implies infinite scattering. And this is an old thing by Müller in the 1940s. You have seen already an example like this. This corresponds to carbon dioxide. You have 3 balls here, right? In state 1, that's fluid compressed, right? And now when you go to the critical point, right, the whole thing becomes turbid. Because, why does it become turbid? Because you have density fluctuations that are similar in range to the visible wavelength, which is large. Here, the correlations are those of a gas. So to interact with that, you need a very small wavelength. You have to go to the X-rays. But when the correlations become that big, when the fluctuations have correlations comparable to the length of the visible light, then it interacts and the whole thing becomes turbid. even though it is the same material. If you lower the temperature, again, you have a phase separation. So here, system starts to phase separate, and in the end, in 4, you have an interface here between liquid, gas, and you have the 3 balls floating at the interface. All right? So this is a classical example that tells you, connects the thermodynamics, this point, of infinite compressibility with an optical phenomenon, turbidity, because you have fluctuations of long range, and divergence in the scattering factor, right? If you have fluctuations for non-zero Q, well, if you have fluctuations for non-zero Q, we will see it later, right? But here we have the same thing, but retain the value of Q, right? That's the fluctuation in density. And the fluctuation in density, if you expand these densities, right, taking into account using the Fourier transform of the delta function, here you will end up with exponentials, is precisely that. And I think we have been going over this formula once and again. Fluctuations in density for different Q are just precisely the scattering factor, the structure factor, right? Well, when you have density fluctuations different from non-zero Q, that means that you will have a divergence for a given value of wavelength that typically indicates what is a Lifshitz point, a system where a point where the system becomes unstable against a phase transformation towards a modulated phase. That means a phase in which you will be able to distinguish a distance, a characteristic distance, that is connected precisely with this Q naught. Recall, 2 pi divided by Q naught will give you this modulation in R space. So this is what it's telling you if you have a divergence for a value different from 0. So if you have divergence at 0, critical point. Phase separation, for instance, if you have a mixture, the mixing. But if it is non-zero Q, there will be the appearance of order or something similar. Okay. This is an example of a system we were playing with, a system that forms clusters, using this short-range attraction, long-range repulsion I told you about. And here you see the presence of a pre-peak for a relatively high temperature, practically no structure, that means this is a gas. So you see here there is a marked tendency of clustering, right? And you have the picture here. Let's see if I start it. Right, nope. Let's see how, maybe the hard way. Well, it doesn't want to run. No, it's a video, yeah. It should run.
No, but it's the file you are presenting in PowerPoint or PDF?
No, it's a PowerPoint. Let me check, because this is really weird. Yeah, it's running. Okay. Let's see if I can move the cursor there, and yeah, maybe here. There you have it. Okay. So, what happens when you lower the temperature is precisely this. You have the formation of these huge spherical clusters. They are relatively big. And the scattering, the structure factor goes from this one that is telling you, well, I want to associate but still is not associated, its association is not visible to the eye, to this one here, which is huge. It's almost a divergence, right? And the position of this peak reflects the distance between the clusters, right? Moreover, if you move to larger Qs, and you look at the scattering factor for larger Qs, that you won't be able to see it here. You have to go to see this is Q times 8 times Q sigma, 8 times sigma. You see this structure and say, gosh, that's the structure of a liquid. Well, what this is telling you is that the clusters, the internal structure of the clusters, is that of a liquid, right? And the divergence means the stability towards this modulated phase. This modulated phase, in this case, is just spherical. It's practically a glass, so to speak, of spherical droplets. But depending on density, you could have these lamellar phases, order phases, many possibilities. Always the signature is the divergence at a finite Q. Now it goes, right? Well, let's see a little bit of the Austin-Zernike equation. Austin and Zernike were working a long, long time ago. So you look at the original article, it's hard to connect the formula they were using with the ones we are using these days. But they already knew the concept of pair distribution function and so on, as a measure of correlations. They were using it in scattering experiments. And what they realized when they transformed backwards, they tried to transform backwards the structure factor is that the corresponding G of R was a divergent property because S of Q at Q equals 0 diverges. So they decided, okay, let's look for a function that reflects the structure but is not divergent at the critical point. And they propose this equation that is nothing but a definition. This is the equation that defines the direct correlation function, the C, which is a convolution. And actually, if you take this equation and insert it multiply, as we did, for instance, if you recall with the Schrödinger equation, typical thing that, well, you use H, get an H, and this is inserted here, and this is inserted here. You end up with a series of CR, the integral of CR squared, CR cubed, and on and on and on, with density also in powers. Rho, and rho square, okay, right? This is telling you that C of R, in the end, will represent direct correlations between two particles. And this is the pair distribution function minus 1. It's typically called total correlation function because it includes direct correlations, correlations mediated by one particle, by two particles, three particles, and on and on and on. That are the terms that you get here when you do the expansion, right? If you do the Fourier transform of this Austin-Zernike equation, right, you get this. And if you look at the limit, if S of Q goes to infinity, C of Q goes to 1 divided by rho. That means the direct correlation function does not diverge at the critical point. And this is a very, very important property, right? Actually, if you look deeply into that, this quantity has a property that its limit when R goes to infinity is just precisely minus the interaction. That's the reason why typically it's a measure of the interaction, right? And it's always divergent with one exception. It's always convergent, sorry. You can always integrate it. There is one exception that has to be treated with care. Coulombic fluids. Why? Because here, for a Coulombic fluid, you have 1 over R. And you cannot Fourier transform directly and happily something that goes as 1 over R because it diverges. Coulombic fluids have to be treated carefully. In the end, you can do things because in Coulombic fluids, in salts, you have screening. So Coulomb interaction, when you have more than one particle, is screened and two particles separated each other by a medium, do not see the bare Coulomb interaction. See a Yukawa term, a Yukawa interaction. Okay, let's take a look and see that the structure factor can also be understood as a response function, right? To that, well, one defines this term, that is intrinsic free energy. That's density functional theory. And for the intrinsic the free energy, we have a term that is intrinsic to the system. And this is the term, the contribution from the potential, the external potential and the density, right? You have an intrinsic chemical potential defined in this way, right? And you can use the functional differentiation in this way, that's the definition, right? To get, okay. If you perform the functional differentiation of the ground potential, it was defined here as the free energy minus n times the chemical potential, you end up with the density. If you perform the differentiation with respect to psi, the potential, you end up with this function h. If you perform two differentiations, you end up with h to r that actually is this quantity. This quantity is the pair distribution function. Well, this is connecting once more thermodynamics and structure. Well, with this, in the end, this is a typical equation in linear response theory. You have a perturbation that acts on the, that ends up in a fluctuation in density, and here you have the response function. Well, this response function is this quantity, right? And the response function to this fluctuation ends up being precisely this term, and this term was the fluctuation of density. So that is the important quantity, and it's called the fluctuation dissipation theory. The limit of Q going to 0 is the isothermal compressibility. And it's telling you that this is the response to a field that is the source of fluctuations in density, right? You say fluctuations in density, the field that makes the fluctuations, and the function that controls the response of the system. The function that controls the response of the system is this quantity, whose Q0 limit is precisely the compressibility. And in the Q0 limit is easy to understand, right? In multi-component systems, you have to be careful how you build them. These are the responses, and this is the expression for the isothermal compressibility, right? That's the equation you have to take into account. If you want to, if you have partial structure factors and you want to calculate the full isothermal compressibility, you have to take into account all the components. It's not the Fourier transform of the full structure factor. It has to be built in this way. And this is something tricky, right? So keep this formula in mind. It's already pretty old. All is due to Kirchhoff and Buff. And that is controlling precisely how the system responds when you have very many densities. This is important to check other types of fluctuations, and is used quite a bit in mixtures, mostly in binary mixtures. And you will see they are called the Bathiat-Thornton structure factors. These people, they propose the use of, on one hand, density-density fluctuations. This we already know. But they also introduce the concentration-concentration fluctuations, right? In the case of binary systems, they are simply end up like this combination of partial structure factors. Why is this useful? We have seen that when Q goes to 0 in a single component system, if there is a divergence, you have a critical point. What happens when you have two-component systems. You have two-component systems, you have the possibilities of two types of critical points. One is just the liquid vapor. The whole system goes into the vapor phase. But the other one is the mixing. The system can separate into phases, right? This is precisely what is being monitored using the concentration structure factor. Because this quantity actually is the response function to something that the field that originates concentration fluctuations. Before the mixing, the system starts to have regions in which one component is more concentrated than other. These regions become larger and larger. Finally, they become microscopic until the correlation length diverges and it separates into two phases. For instance, two different liquids. So, oil and water. You may have at a sufficiently high temperature. Well, oil and water is a bad example because they go into the vapor phase and before mixing. But some other liquids, organic liquids, can mix up to a certain temperature, and if you lower the temperature, they separate, right? If you monitor these quantities, you can see that there is a divergence here that indicates the phase separation. And here you have an example that is just obviously a simulation. This is the sort of the beginning of the end of the mixture. You start to have domains. The domains increase, and in the end up you have large separated domains. And if you look at the concentration structure factor, here you have what happens when you increase in this case I think it was you lower the temperature or increase the concentration of one of them. Sorry. So here it's relatively small, practically nothing, and then blows up. So you end up with two phases, right? This is a demixing that is induced not by changes in temperature or pressure, but by changes in concentration. One liquid sometimes accepts another up until certain concentration, and from that concentration onwards, it separates. So this is what happened here, right? The other quantity that I didn't mention is the cross quantity, the density concentration fluctuation, which is, well, not that interesting. I mean, you could take a look at this in the case that the mixing and vapor-liquid transition are associated. That might be the case in some instances. Well, the formula moved. Well, simply recall that divergences for Q going to zero are phase transitions. Divergences for Q different from zero. The emergence of specially ordering modulated phases. Let's see, what time is it? Okay, let's make a break now. Yeah, 10 minutes before we go into the reverse Monte Carlo. Fourier transformation. But Fourier transformation is not always possible. Not always we can do isotopic substitution to separate components. So we have to resort to some alternative technique. Well, the technique of choice for most people working on this problem, although sometimes there's much discussion about it and the results you obtain with it, is reverse Monte Carlo. Reverse Monte Carlo was proposed by McGreevy back in the 80s. I think it was the late 80s. So it's a technique that has already more than 30 years. And the idea is to go from the structure factor to a microscopic configuration that is described by pair distribution functions, right? Additionally, strictly speaking, the inverse problem many times is considered going from the structure to the calculation of the interaction potential, right? So this is tricky depending on the definition you use, but both things can be considered inverse problems because you have to go from reciprocal to real space. Okay. The alternative to inverse Fourier transformation, that as you see here, you have the limited range of Q, for instance. To do a good Fourier transformation, and we will see that in the hands-on, you have to have a large Q. Not all the instruments produce have this large momentum available for sampling. And typically, when you go to large values of Q, the uncertainties are much bigger. And this accumulates a lot of error for small r, right? And the additional problem that I mentioned several times is the limit availability or the price of isotopes. So you can go to molecular modeling. That's either Monte Carlo or molecular dynamics. The problem is that there you have to have a reliable potential. And not always you have potentials that you can rely on. Otherwise, you go to first principle. Okay, now we have large computational resources, and we go to ab initio calculations. Well, ab initio calculations are tricky, depending on the material. For some materials, you can hardly do it. For instance, if you have transition metals with F electrons, you are in serious trouble. And if you have complex molecules, you are also in serious trouble. Water is hard to deal with because of the hydrogens. And interestingly, all these methods, they were designed with things like semiconductors or metals in the head. So one of the big problems that ab initio methods have is dealing with van der Waals forces, with dispersion forces. So if you have something as simple as, say, carbon molecules interacting with each other, if you do ab initio for a single molecule, fine, you will get everything. And this is what is called computational chemistry. You can get to all the level of accuracy you wish. But when you have several of them, they start to interact with van der Waals forces, with dispersive forces. Some of them come from the fluctuating dipoles, from the fact that the electronic cloud changes polarizability. The electrons move. So you have a dipole that on the average can be 0 or has a certain value, but is constantly fluctuating. These fluctuating dipoles are the origin of the van der Waals forces. And to implement them in ab initio calculations, you have to resort to corrections. So there are a set of corrections, like Grimes corrections, that are relatively good, but they are still kind of empirical in a way. So these are some of the problems you have in ab initio. Also, of course, there's a lot of research trying to improve the methods. Still, it's very expensive, computationally speaking. Getting up to 1,000 molecules, well, it really is very, very costly. So it's the last resort. So, and if you have large samples, forget about it. I mean, the samples I show you of the clusters, this cluster formation, are using 200,000 particles. You can't do that with ab initio. Forget it. No way. So for properties that depend on large number of particles, there's no way. Okay. So here comes the idea of reverse Monte Carlo. Reverse Monte Carlo actually is connected with a minimization problem that was established many years ago for a technique that is called simulated annealing. Simulated annealing is the last resort when you are trying to optimize a problem, particularly a problem in which you do not have a continuous variable. There is a typical problem that's called a traveling salesman. That is a guy who is a salesman, has to visit many cities, right? And you have to find the optimum path that he has to do, path and direction, to travel the less possible distance. Obviously, since the cities are a fixed distance, the function that you have to minimize is not continuous because it has discontinuous jumps between them. So you cannot use standard methods like gradients or any typical method that is that either you have to use an stochastic method. So if you look at simulated annealing, it will be very similar to what I'm going to tell here. Actually, it will be like a zero temperature reverse Monte Carlo. In this case, let's see, we want to simulate a function. We have this quantity as an input, the structure factor, that we have measured and cleaned of all this messy multiple scattering and all strange effects. And we will put a sample in a simulation box, typically a periodic simulation box, in which you have point particles. And with these point particles, we calculate the scattering, the structure factor, the corresponding structure factor. Okay? This sigma square here is the uncertainty in the experimental structure factor that you can actually estimate from your experiments. And you have this chi-square objective function. So actually it's a multiple variable minimization process. Why is multiple variable? Because the variables you have to minimize are the position of the particles, right? So you have to move the particles until you manage that this quantity is minimum. And this position will be the spatial configuration that is most compatible with your initial structure factor. Okay, what's the algorithm? Well, you have your original particles, and you perform a random displacement, right? With this random displacement, you calculate the delta square trial, right? If delta square, this chi-square, sorry, the difference in chi, is less than 0, that is, the objective function goes down, you accept the trial, right? If it is greater than 0, you can reject it, but then the system may easily get stuck, or you use a probability like this. With a simple factor 2. In the traveling salesman problem, which is very similar, and you can do that here as well, what you use here is an effective temperature. Why do you use an effective temperature? I tell you why. Because if you end up in a position that has a local minimum and you have a certain temperature, you have a probability of jumping over that minimum. If your temperature is fixed, you may be stuck because the maximum of this valley in which you fell during the process of looking for the minimum may be too high. So you start with a relatively high temperature and sample as much as possible, and then you start to lower the temperature. In the end, you may end up with 0 temperature. 0 temperature, that means that all moves that have this greater than 0 are rejected. Because 0 temperature, that's 0 here. All these probabilities, okay. What are the caveats for this method? First, you have to define a core. particles have to have a core, because otherwise you will have overlaps that will mess up things, and you don't want particles to overlap. This core that you introduce is kind of artificial. So you go to the periodic table, look at the van der Waals radio, and you use something similar to that, sometimes smaller. But this is a variable that you have to do dirty chemistry with it. Something that is completely, you have to have a feeling for the course. And, well, it's something that many people do not like. Okay. Most of the times, you have to introduce chemical constraints. I mean, if you are trying to do, for instance, a reverse Monte Carlo, and one of your molecules is carbon tetrachloride, that is C and 4 chlorine atoms, you know from chemistry that they form a tetrahedron. You do not let the reverse Monte Carlo to go blindly with the positions of the chlorines. So you fix the molecule and move the molecule as a whole, right? Or sometimes you know that certain atoms like carbon prefers certain type of coordination, fourfold coordination. Then you introduce a bias to sample in the direction of fourfold coordination. This is one of the critics typically, those that do not like reverse Monte Carlo, they focus their critique on this type of things. Because this type of things is more like a feeling, an art. It's not something that you have a definite criterion. The only definite criterion is this one, which is okay. That's a Monte Carlo, a metropolis criterion. But you need additional things, or otherwise you will get multiple answers, right? Why do you get multiple answers? Because this is a method that does not have energy there. It does not minimize energy. It doesn't know anything about energy, right? So what is the quantity that actually is not minimizing, it's maximizing? Entropy is maximizing disorder. Because the only thing that you are actually doing is moving the particles, trying to fit a function. And with all the possibilities that you can use to fit the function that is a pair function, that means it contains only information about pairs, right? It will maximize the entropy. So it will give you the most disorder structure possible. But you have to live with what you have, right? You can use a hybrid approach if you have some idea about the interactions. If you have some idea about interactions, what you do is you start with an initial structure, you refine the structure, use the reverse Monte Carlo, which maximizes the entropy, and here you put a force field, and you do a molecular dynamics or a Monte Carlo, and you minimize energy. And in this way, you get a system in which both things are satisfied, right? Both criteria. Problem here, you need a reliable force field, not always available. And you have to iterate the procedure until the whole thing converges. We did that some years ago to study this system that is a carbon nanosphere that we use from chlorination of cobaltocene, which is sort of a sandwich. And that was treated with chlorine and then put in an oven, and then you end up with these spheres. But these spheres have a structure inside. And we wanted to know the structure of the spheres inside. So we performed a series of experiments, right? And we found, for instance, that these peaks that we got in our neutron scattering experiment were matching the peaks of graphite. That means, gosh, we have the structure of graphite, but there is disorder. You can see there, you don't have the perfect layers that you have in graphite. But there are layers, right? So there must be some sort of pi-dimensional orders with finite layers. So what we did, we built a system with layers, like that. We started to disorder the layers. And then we put a field here, right, between the layers, actually a potential, and the layers started to twist to connect with each other, right? And we use the reverse Monte Carlo here, so to obtain an entangled structure. The final structure, after iterating between the reverse Monte Carlo and the molecular dynamics, was this. So you see the layer structure, you see the hexagons, typical of graphene or graphite. You see some remnants of the layers. And when you compare with the structure obtained from high-resolution transmission electron microscopy, well, you get something that looks like that. Okay. The sad part of the story is that when we perform absorption experiments, our system was too tight, too narrow compared with the experimental one. The experimental one had larger spaces to absorb gases. So you're going to go further. You have to implement something in your reverse Monte Carlo system that actually uses absorption information, which is highly non-trivial work to do. So, but again, from the point of view of comparing with the electron microscopy, the results were rather interesting. Okay, this is the useful package. This is the basic package from reverse Monte Carlo, which is, it's control, develop, and managed by a group in Oxford that took everything from McGreevy originally. There's people in Budapest contributing to that, with whom we have collaborated. So if anyone is interested, except for a special application, do not develop your own code. Use this ARM and C profile. Other alternatives. Well, one of the big guys in neutron diffraction, Alan Soper, proposed this empirical potential refinement structure, which is rather similar in a way to the hybrid method that I mentioned before. Basically, you assume a form of the potential, but you have to assume a functional form of the potential. You put a lot of parameters, and you do a sort of minimization of these parameters using an stochastic approach, a reverse Monte Carlo-like approach, but not on the structure. Now the parameters are not the particle positions. The parameters are those of the potential, whose functional form you already know. We fooled around with these methods quite a long time ago, a late colleague of mine, back in 20 years ago already. And we proposed this inverse Monte Carlo that has the advantage for simple systems that gives you a form for the potential, a functional form. So you don't have to assume a form, but they gives you a form, and you can put additional constraints if you know the energy of the system, if you know all the properties of the system. You can get that, or you can even optimize this work that, stopped for set reasons, but we were about to implement the three-body interactions there. But these are inverse problems. Okay, before we finish, just a word of warning, which is important. All those approaches that are based on the generation of effective pair potentials, and this is what is called the inverse problem, getting a potential which is pair from the information of the structure factor, are tricky. Only if the system under study has strictly pairwise interactions, you have a complete univocal correspondence between the G of R and the U of R. And this is mathematically proven in Henderson's theorem back in 1974. But if your system has pairwise interaction, obviously experimental systems have very much complicated interactions. Even if you are using noble gases, you have three-body interactions. Most of the interactions can be described pairwise, but they do have three-body interactions because they have triple dipole interactions, right? So This is telling you that you have to be extremely careful because you may get a potential. The potential gives you a structure factor that fits exactly what you are, your structure factor, the experimental one, but the structures you get are awful. We did the experiment using selenium. I mentioned before that selenium is an interesting subject because it forms chains. So we did the inverse. We got the potential that reproduced exactly this interaction. I don't know if we can go back because I think it was somewhere here. Oops. Yeah. Just to recall, here you have liquid selenium. So the structure factor is rather peculiar because it has this pre-peak that comes from the chains and so on, right? So our potential for selenium reproduced that exactly. When we started to look at the configurations, we obtained, in addition to chains, 4 like squares, which are not existent. Selenium can form chains or rings, but never 4 particle clusters. We obtained a system that was compatible with 4 particle clusters. So why? Because our input data was ab initio calculation for selenium, which is essentially many-body. You have 2, 3, 4-body correlations, right? If we were able to introduce a 3-body term, then we would also be possible to restrict the system to chains, right? But you need this information from other sources, from beforehand. Only the structure factor gives you very little, right? So I hope you get the message today, and tomorrow a little bit more, okay?